So this homework, if you don't have the 4-2 homework done, it's due tomorrow. So if you don't have it done, that's your homework tonight. I want to go through this example together, kind of refresh everything that we have been doing. So here's my data. If I ask for a scatter diagram, what am I doing? Yeah, so I'm going to count by twos for my y's. Okay, so you plot your points. So we have 2, 4, bless you, 4, 8, 6, 10, 6, 13, and 7, 20. All right, so then if I want to use my calculator to find all this, what do? Stat edit. All right, so my x is 2, 4, 6, 6, 7. My y is 4, 8, 10, 13, 20. Then we go to calculate. We can do 2 variable statistics just to get everything at once. So x bar is 5. Standard deviation of x is 2. Y bar is 11. Standard deviation in y is 6. Everybody with me so far? All right. So if I asked you to find the correlation coefficient by hand, then I would give you this big table, and we just have to fill in all this empty places. So we have my x's 2, 4, 6, 6, 7. Y's 4, 8, 10, 13, 20. So then, on my calculator, I'm going to do parentheses. My x, which is 2, minus x bar, which is 5, close my parentheses, divided by standard deviation of x was 2. So negative 1.5. Okay, and we're just going to go through and keep doing those. So the next one, put in a 4. Next x is a 6. Another 6, and if you put in a 7, we get 1. You guys know where I got all those numbers? All right, so then we do the y's. So your y value, minus 11, divided by 6. Alright. So does everybody know where I got all my y's? Now what do? Multiply. I'm just going to write down what all of these are. So you're just multiplying these two numbers for each one. So we get 1.7501, 0.25, negative 0.0834, 1667, and 1.5. All right, grab your formula sheet. So we are finding R. So look on your formula sheet. First thing under chapter 4, the first bullet. Correlation coefficient. It has this big symbol. That's the sum of all of these. So if we add those up, we get 3.5834 divided by n minus 1. N is the number of ordered pairs. So we have 1, 2, 3, 4, 5. So 5 minus 1 is 4. So we get an R value of 0.89 9. Does everybody know how I got that by hand? So next, I want to know if there is a linear relationship between x and y. All right, so let's make sure. Go to table 2. So second piece of paper in your formula sheet, back of that. The critical value. N was 5, so my critical value is 0.878. Remember, if the absolute value of r is bigger than the critical value, that means it's good enough to be linear. So my r was 0.8959. So the absolute value of that, is it bigger than 0.878? Yes. So we have a linear relationship. And that is my justification. Not just me saying, oh yeah, that's close enough to 1, it's probably good. I can verify. Is it a positive or a negative linear relationship? Positive, because r was a positive number. All right, how do we find the regression line? Stat, calculate number 4. We'll give it to us on our calculator. Let's say I wanted to do it by hand. We have all the information already. So if you go back to your formula sheet, second bullet, okay, it tells us b sub 1, which is the slope, is r, which we got 0.8959, times standard deviation in y, which was that 6, divided by standard deviation in x, which was 3, I believe. And so we get 2.6877. The y-intercept is y bar, so it was 11, minus the slope, times x bar, which was 5, and that one was a negative 2.4385. So we get the regression line, remember we usually call that y hat, is 2.6877x minus 2.4385. Let's verify it on our calculator. So if you go to stat, calculate number 4, it tells us y equals ax plus b, a 2.6875, b negative 2.4375. Why are we slightly off? Rounding error. But we're pretty close. So it's a pretty good estimate. Any questions there? Alright, F. Use the line to predict y when x equals 4. So we're just going to plug in a 4. And I get 8.312. Final question, residual. Anytime you forget what something means, go to your formula sheet. It's right there. It's observed y minus predicted y, or it tells you y minus y hat. We're looking at when x is 4. So if you go back to the original data, when x is 4, the actual y value was 8, minus the y hat, our predicted when x was 4, 8.3123. So we get a negative 0.3123. So that's how far off. Our prediction was that far off from the true value. Any questions there? Alright, so trying to kind of tie in all the scatter plot and linear regression stuff we did last week. So just thought it would be a good problem to start us off with. So I want to take the rest of class. We're going to look at the next section. I did print notes for you because I'm talking about a lot of diagrams, and it's just easier if you already have them in front of you to look at.
Do we need to in front of us?
You don't have to. It's extra practice for you if you want to do it, but I'm not going to grade it. Printed notes. It's the little things in life, right? Okay. So, diagnostics on the least squared regression line. We know how to find this regression line. And we know we can use, take our data, we can get a line of best fit, we can use it to make predictions. We've seen where we can see how good of a line it is by finding the R value, the correlation coefficient. We know the closer that is to positive or negative 1, the better the linear relationship. This is just going to give us a little more information. So we are talking about the coefficient of determination today. It is on your formula sheet. They call it capital R squared, but it's the same thing as R, lowercase r squared. So remember when we do these diagnostics, like when I went to my calculator and did a linear regression, it tells you A equals B equals R squared equals, that's the coefficient of determination. And what it's telling us is the proportion of variation in the response that's explained by the regression line. So for instance, on that problem we just did, if I look at the R squared in my calculator, it's 0.8025. So that tells me about 80% of the variation in Y is explained by my regression line. Okay, variation in Y. So we know not every Y value is the same, right? We want to know why are they different. Okay? If you think about it, if we have a true line, then all the Y values should be different, right? So if your R squared is a 1, that means 100% of the difference in those Y values is because of the line. It's because they're giving me different points on the line. Okay, if I have an R squared of 0.9, 90% of it is because of the line. 10% is something else because points aren't exact, that kind of thing. Just kind of like when we're looking at linear relationships, 1 is really good. When R is close to 1, that would correspond to R squared being higher. It's always going to be between 0 and 1 because we're squaring a number, so it won't ever be negative. So we are just going to be looking at that. It's very, very closely related to what we've already been talking about. So when I'm talking about deviation, deviation is just how values are different from the mean. Okay, we can find our Y bar on that worksheet we just did. The mean in Y was, what, like 11 or something? But not every value was 11, right? So deviation is how they are different from that mean. Explained deviation is the variation that is explained by the regression line. Okay, different points on the line, we expect them to not all be the same. Unexplained is other factors. So, let's just practice in R squared and writing a sentence to explain that. If you are looking on your formula sheet, it also tells you exactly what R squared measures, the proportion of total variation in the response that's explained by the regression line. So it tells you on that formula sheet what it is. An example we've been using throughout this chapter was our oil or rock drilling example. Okay, so let's find R squared for this data. So if we go back and we put that in our calculator, you do have to make sure your diagnostics are on, which hopefully they are for everybody. And then if you go into stat, calculate your linear regression. We want the coefficient determination, so we want R squared. Everybody get 0.5973 for R squared. Okay. So what this means, it's telling us the proportion and variation. So what we could say, if I had to explain this, is 59.73% of the variation in Y, which Y was the drill time, is explained by the regression line. That means over 40% of this variation is due to something else. So this was probably not a great linear model. If we looked at this one, the R was 0.77. We said 1 is perfect. So there is a relationship, but it was not a super strong relationship in this data. The next slide, I just showed some pictures of what the different scenarios might look like. Data set A, we can see the line and the points are very, very close. So that would be when almost all of the variation is due to the regression line. So that would be like an R squared of 99.99%. B, they're a little more spread out. That one was 94.7. C, we could see there's really not much of a linear relationship at all. That one only 9.4%. So the less linear it is, the smaller your R squared value is going to be. All right, the main thing that we're doing in this section, though, is what's called a residual. So the residual, we've already looked at, was observed minus predicted, right? So when we are looking at those, we know that our line is not going to be perfect for all the actual data. If we want to see how good of a linear relationship it is, we can compare the residuals to what we would expect. We are going to use a residual plot to check to see if a linear model is accurate. There are situations where we might get a pretty high R value, but there's actually a pattern in the residuals. So it might be the case that our line is a really good predictor at first, then it's really bad, and then it's really good again. So something else may have been better instead of a linear model. When we are looking at residuals. There's basically three things that might be a problem. If we see a pattern, that's bad. So this one, these are the residuals. So if I went through every actual ordered pair and found the residual, so observed minus predicted, and plotted those points, we don't want to see any pattern in that. So this is pretty good because they're all kind of random. We have about the same positive and negative. This one's bad because we can see there's a pattern to it. It was pretty far off at the beginning. The middle of the data, it wasn't too bad, and then towards the end it starts being off again. So that would be a poor scenario. Let me show you how to plot a residual plot. So first we're going to enter this data into L1 and L2. Did you guys all get that entered? Let's look at our stat plot first, just to kind of get an idea. So stat plot, turn on, scatter plot, X is L1, Y is L2. We go to zoom 9. So does this look linear? Yeah, it looks pretty linear. Let's check the equation. So if we go to stat, calculate, linear regression. Okay. This is looking pretty promising right now. My R, negative 0.994, isn't that almost an exact? Yeah. R squared, that means 98.8% of the variation in Y is explained by the line. So those are all looking very, very good. If I want to look at the residuals, so we are going to go to second, stat plot. Go back into plot 1. For each point, for each of these X values, we want to plot the residual, the difference in what we actually saw versus what the line would give. So on the Y list, you need to go to second, stat, and number 7 here is residuals. I think on these calculators, does it have another option? One of mine I looked at had. So everyone find the one that said residual, number 7. Okay, so then if we go zoom number 9, what do we see here? I have another line accidentally I didn't delete out on here. So my R was really close to 1, so it's a very linear relationship, but I am seeing a pattern in my residuals. Now that doesn't necessarily mean that it's not linear, but what it means is there's a pattern with what my line does. At the beginning, the line is what? How would you explain this? Okay, so it was started out positive, it went negative, and then it ended positive again, right? So observed minus predicted is how we got this. So it basically means at the beginning, for the lower values, what I saw was higher than my line actually expected. Then in the middle, my line was higher than what occurred, and then at the end, it went the other way again. So we can see this pattern here. So that would be an issue that we would need to consider if we were looking at this. So we have basically we have an overestimate at the beginning and end. Underestimate in the middle. So we have a clear pattern here in these residuals. Mm-hmm.
I don't know, whenever I try to graph it, it just changes there.
Okay, did you run the linear regression? So one thing that always comes up, and I'm glad you mentioned that, before it can find residuals, you have to tell your calculator to find the regression line. Because it doesn't save that line into its memory unless you actually run it, and residuals are based off that line. So you always have to do the linear regression first, then you can plot the residuals. Okay. Another thing to look at with residuals is what's called constant error variance. You know, if I look at this, this is a good plot, it looks like, but if I look at my residuals, I can see over time what's happening to my points. They're getting further away from the actual line. So it's a pretty good model at the beginning, but not as great of a model as time goes on. So we have to look for patterns. We have to look, does it violate constant error variance, which means it's basically better at predicting at one point than another. The last thing we can look for on the residual plot is outliers. Outliers would be when we have something far away from the other, so this is the original scatter plot. And then when you look at the residuals, you'll see all my residuals are pretty much right here with the exception of that one. So you can kind of catch those outliers on residuals as well. All right. Let's go ahead. We're going to go ahead and finish this, and then tomorrow I'm going to give you guys time to work in class, okay? So if I wanted, it would have been nice if I did this before I had to put in a new one, wasn't it? That was rude. Sorry. All right, go back to our drilling data for like the 7,000th time. All right. I should really change the order of those examples. All right, so if we put those in. So we have to look at the linear regression first. So we have to go to calculate linear regression so that it has an equation for our line. I think I might have mistyped a point. It's okay, you guys have got it all correct, right? So then to get our residual plot, if we go into second stat plot, you notice mine is already set. It saved your last setting, so it says L1 and residuals, so this will be our residual plot. So if we go to zoom number 9, I need to clear out what's there. Okay, so here is my residual plot, except I do think I have one data point off. So what does this look like? Do we have any outliers? Not really. Is there a clear pattern? No, that's good. We don't want patterns. Does it violate constant error variance?
Yes.
Somewhat. It's not like a massive difference, but we can kind of see a little bit of a spread there. We don't have as many points, so it's kind of hard to tell for sure. So you could say this is a little bit violates the constant error variance. So the linear model might be okay, but it's not great in this scenario. Last thing I want to look at definition, an influential observation. Influential is just a point that would significantly change the regression line. Okay, if we look at these, in this data, I have 3 outliers. Here's an outlier, here's an outlier, here's an outlier. If I were to think about my regression line, it would probably go something like this, right? So would case 1, do you think that would, it's clearly an outlier. Do you think it would be influential? Would it change the regression line much if I put it in there?
Yes.
Probably would. Okay. Now, hard to know for sure. What we could do is actually look at the regression line with and without it and verify that way. But it looks like it's fairly high above the others, so it would probably shift our line up some, so it might make a difference. What about the second one? It's an outlier. Would it be influential? No. It follows the same pattern. You know, if we continue our line, we're basically going to hit that anyway, so it really wouldn't change our line much. What about case 3? Yes, this would be influential for sure. It would bring our line down quite a bit. So all of these are outliers, but we can see some outliers will affect our data more than others. All right. Real quick. So if you go to your drilling data that we have entered, let's write down our regression line right now. So your current regression line is what? What do you have for A? Okay, X plus B is 5.5. Okay. Now I want to see what happens if I add in a new point. So I'm going to go to my table. I'm going to add in one new point, 300 for my X, and my Y is 12.49. So now let's look at the regression line. What does it become? Plus 4.4433. All right. If we really want to check if these are different, we could graph them both. So if we go to our y equals, we'll put one of these in y1, one of them in y2. I know I'm almost out of time. In our stat plot, let's go back and change the y to L2 and then zoom 9. So that should give us our scatter plot and the 2 lines. And what we're really looking at, do these lines look significantly different from one another? So I have the first one is like this and the second one goes like this. Is that a big difference? I mean, it kind of depends on what we consider a big difference or not. There is definitely something, isn't there? So what we would probably say, is this point influential? I would say yes. It did kind of change my line. It pulled my line up quite a bit.